like a perfectly valid reason to just stay home. Sorry. How y'all doing?
It's Friday.
It is Friday. And, lost my train of thought already. Is that a good sign? It's probably not. I don't know. What are words? It's test review time. Test starts next week. Before I get into all that, does anyone have any questions? Most of the day is going to be review for said upcoming test. So if you say have any homework questions as well as test specific questions, do please ask them. Yes?
Are all the labs in the same lab room?
The labs are in the same lab room, but for the test you should come here, just because there's more space.
Yeah.
So
We still have a lab next week?
we don't. If I haven't said that out loud yet, there's no lab next week. Instead, you will come here to take the test. There is no lab next week. But during lab time, you come to this room to take the test. Does that make sense?
Yeah.
I like to use the lab slot for the day so that you can take it in a nice, comfortable amount of time and not have to rush in and do an hour-long test in 50 minutes.
Will there be an issue with space, like if everyone decides to do it on Friday?
There shouldn't. Friday is normally the smallest lab section anyway, so there would only be not enough room in here if everyone decided to do it Friday, and I know for a fact there are some people that just want it over with on Monday. Yeah, sorry, I'm getting ahead of myself. So yeah, test is happening over the course of next week. You will take it during a lab time, that's 1:30 in the afternoon on either Monday, Tuesday, Wednesday, or Friday. Thursday does not exist, Thursday is a myth. During one of those afternoon lab slots, you will come to this room to take the test. There is no other lab next week to have to worry about. So it's just the test. And since the test is happening in lab, we also have lecture to review. So say if you did take it on Monday, October 2nd, lecture that morning would still be review time to look at the practice test where I would answer any questions from anyone about the stuff they've been working on. And then the earliest you would take the test would be that afternoon at 1:30. But again, you could take it any of Monday, Tuesday, Wednesday, or Friday afternoons. Thursday the 5th is the one afternoon where the test will not be administered. So if for some reason you had in your head you'd do it Thursday, no you won't. That said, what am I trying to say? If you can't make any of those days, like, sports or health concerns show up, I can figure out some other time that you could take it. If you miss the test and can't make any of those normal days, you'll be able to make it up, I promise. Now, once you take the test next week, you basically have the rest of the week off, because lecture is test review, and if you've already taken the test, then you don't really need a review for it. You can still show up. I encourage people to show up, but if you take it Monday, Wednesday and Friday lecture, optional. Start your fall break early. Yes.
Now, will you be grading these over fall break?
Yes, I will.
Okay.
My plan, my guarantee, is that these will be graded by Friday morning, the 13th. Because midterm grades go out that morning. So I am ordering myself to have them done by then.
Scary midterm. Scary midterm.
Scary. Is it scary because it's a physics midterm or scary because of the day? The day?
All across the board.
Oh, that's fair. It's physics. It's scary. That is valid. Now that said, what the midterm score for this class is going to be is your current average. It's not just going to be the test score. On Friday, when you show up for lecture that day, I'll give you your test back. It'll be done by then, and once I give you your test back, it is yours to keep. You'll see how you did on it. I'll cross out what needed fixing, and then we'll spend the day looking over my answer key and making sure everyone's comfortable with how things went and understands what I was looking for. And once you have your test, it is yours. You don't have to give it back. You can keep it largely for the purpose of studying for the end of the semester, because the exam is basically test 1 and 2 combined. So you can keep test 1 and study for the exam. So I'm planning on that big give everyone their test back day to be Friday the 13th. And again, midterm scores will go out that morning. It'll be based on your current class average, which is going to be the test, the homeworks, the quizzes, and the labs. That said, this school's midterm system is really just S for A through B and then D and F, which means that I have a ton of students who get an S who want to know their actual score, and I will happily tell you that score. It's just the system I have to input them into reduces it down to S's for C and above. So if you get an S and you want something more specific than that, I can give you that information. You'll just need to ask me for it. This one thumbs up. And the test itself, when you come in next week to take it, it is 9 questions, 105 points, graded out of 100 points. There's bonus points built in. There's more questions than you need to answer to get a full 100 points on it. I do this rather than a bonus question because if you don't know the bonus question, then you just kind of miss out. So there's just points built in. Each question will tell you how many points it is worth. So say one of them is worth 5 points. That might be a clue that this one's meant to go quickly and don't stress about it too much. If something's worth a lot of points, then feel vindicated if it's taking you longer. And for every single question, I give partial credit for every single thing you write. So the only way to get a 0 is to leave everything blank. The tests are weighted such that as long as you are trying to give an answer for everything, it's pretty easy to walk out with a minimum 50. Again, as long as you're trying. If you're, sorry. As long as you don't leave anything blank, it's pretty easy to walk out with a 50. And it's weighted so that honest attempts average between C to A. And honest attempt includes not only math, but also writing out paragraphs of science information if you are stumped on what math to do. Anything that will indicate to me that you understand what's being asked, even just conceptually, earns you points. If I ask you for math and you give me a paragraph about how the laws of motion work, that is an answer, that will give you points. That said, if you are stumped, I encourage you to ask either me or Dr. Edwards, who will be in the room. We'll be here to make sure that you, at minimum, understand what is being asked of you. I want to make sure that the questions are clear. And so if you have questions, please ask them. And then if you are still stumped, start writing out what you do know, formulas, concepts, and honestly that jumpstarts the math solving problem sometime. So if you've got nothing, just start writing. Legitimate advice. I say these things as a comfort. Any questions thus far?
No formula sheets used with the test, right?
No, you have your formula sheet. You have your formula sheet.
Sorry.
It's okay. Your formula sheet is meant to be the thing you have access to for the entire class, including any notes that I told you to put on it. Write all over the thing. The only things that I would ask you not to write are, like, don't write out the literal laws of motion, because the point of the test is that I want you to be able to identify them. Not write them from memory. You don't have to like do a spelling bee thing for me. You just have to be able to identify them. I
So
would
if
write,
we wanted to write the quadratic formula,
that's fine.
um,
Yeah, that's not on here. Weird. Yeah, you should definitely write that. You should also write Sokotoa, King Henry died by drinking chocolate milk, and these things. These triangles represent the relationship between normal force and gravity on an incline. If this isn't on your formula sheet yet, it should be. Also, I told you a few absolute value brackets to put on here, namely in the GPE formula. Question, yes, sorry.
Did you say at one point that the laws of motion stuff was like a matching thing?
Yes.
We're not supposed to write it out?
I'm going to list 5 statements. You have to pick which ones are laws of motion and number them accordingly.
Okay.
2 statements will not be laws of motion. They will either be false or they will be other physics principles that aren't laws of motion. You have to identify the 3 that are and actually write the correct number next to them.
And how many questions total are on the test? That counts as 1, right?
9. That's one of the 2 not math-based questions. I'm always I try to be very direct in telling students that that is an expectation of them. I'm trying to be as not vague as I can because when students are scared, vague answers makes them more scared.
Will you have extra calculators?
I only own 1 calculator, and so that means that I only have a maximum of 1 to loan out to the first person who asks, and that's on the days that I'm here. So please do, official request, have your own scientific calculator that is not your phone. It cannot be a phone, it cannot be Wi-Fi enabled, and it has to have sine, cosine, tangent buttons. And if you don't have one, you're at the mercy of whether or not I am there to loan you my 1 single calculator. And optionally, you can borrow a classmate's if you're taking it on different days of the week. So, now's the time to make friends if you don't have a calculator and haven't made any yet. That said, again, it doesn't have to be a Texas Instrument like this. It can be like a Walmart purchase as long as it has sine, cosine, tangent buttons and can handle square roots. I've also seen used ancient Texas Instruments in the tech case at 2nd and Charles, if you live in Columbia. Sorry?
There's one in Greenville too.
Ah, good. Yes.
actually, when we get to the review talk, I'll ask it.
Okay. Well, I think that's all of the technical information about the test itself. So we're entering review stuff now. There's a couple specific things that I have set aside to talk about today. I've got 1 pre-written review example to summarize the last couple things we did on Wednesday. Because on Wednesday we did EPE and power, so I got 1 more example for those things. And then separately, there's also, I keep forgetting how to talk today. It's probably not a good sign. The list of concepts that'll be on the test that I want to go over, just so that you've heard out loud from me what the expectations for each subject are. But before that, I'll ask again if there are any questions about test information or possibly any questions related to the practice test or the homeworks you've been working on. Okay, nothing's coming to mind right now. I do encourage you to bring questions next week, because if you come to the lectures, they'll primarily be focused on answering your questions and doing practice work with you guys. If you don't bring any questions, I'm going to find something to talk about. Question?
Yeah, so with question 5 of the practice exam,
Okay.
dealing with the tension, I'll let you get to it. before I
Yeah.
answer.
Rather than look at bright space, I'm just gonna try to load the file up. Oh wait, I have an answer key already. Let's load that up. So I don't have to open that. Number 5, that's the flower pot tensions.
Yes.
All right, so we've done a few examples of various ropes acting together to try to hold something up. In this specific case, we've got 2 ropes opposite each other holding up a flower pot. And we've been tasked with figuring out the tension in both ropes. Interestingly, both ropes are at the same angle, just opposite each other. And since they're on angles, each rope will have both an X component and a Y component. We don't know either tension yet, but since we know the angle, we can at least somewhat divvy up the unknown tensions into their components. For example, if this is considered T1, T1's Y component would be equal to that unknown tension times the sine of 60,
So,
and its X component would be T1 times the cosine of 60.
so my question was, writing the formulas for tension in 2 dimensions, we have to find the tension in the x-axis and the y-axis.
Yes, because
And
the way that these ropes work together is that their 2 X components are ultimately going to cancel out because their X
yeah.
legs work against each other. And separately in the Y-axis, their 2 Y components work together against the weight of the flower pot. And one does need to look at both of these axes separately, but you do have to look at both of them because the Y-axis one is what ultimately I used to find the tension number, and the X-axis one drives home the point the 2 tensions should actually be the same number, because we see here that their X components work against one another. That means their X components should be equal and opposite, and their X components are both unknown tension times cosine 60. So the cosine 60s just cancel, and that leaves you with T1 equals T2. We don't have a number, but we know it's the same number. And that kind of helps eliminate one of our unknowns, because instead of T1 and T2, now we just have to find T. And so then, taking that information down here, rather than writing in T1 sine 60 and T2 sine 60, it's just T sine 60 twice. Because T1 and T2 are the same thing. And that means it's the same tension in the same spot, same tension in 2 different spots, and they can be combined to get one single number for tension. So both ropes have the same tension, just in slightly different directions. Which is pretty much true of any system where the ropes are balanced but kind of mirrored from each other. Does that help with this one?
yeah, so the equation would be tension equals, tension in the y-axis equals tension times sine theta, and tension in the x-axis is
Well,
tension times cosine theta.
the formula here is technically Newton's second law. Net force equals mass times acceleration. Except one, you would do this twice, once for the x and once for the y. And then 2, when using this formula, say we'll start with the x-axis, one would first note that if you're holding the flower pot up, the x acceleration would be 0. So whatever the net force is, its components must add up to 0. And the definition of net force would be,
The addition of all.
yeah, all the forces present added together. So this is technically your starting formula, and when plugging in specific things, it turns into this. Does that answer the question?
Yeah.
Okay. So that would just be analyzing that in the x-axis, each tension that's present has an x component that is affecting or adding up to the overall x net force of 0. Does that address your concerns?
Yes.
Okay. Any other questions for you guys, from you guys at this particular time? Okay. And as you're studying, please bring these questions to lecture next week. Because if you don't bring something to ask me, I'm gonna find something to talk about. Now, things I have for today, I got one more review example I want to do with you guys to make sure you got just a little bit more practice for what we did on Wednesday. And then we'll look at again the list of all the concepts that will be in the test. So here we have two different baseball pitching machines. One of them is a robot arm with a power output of 1500 watts that is able to load and then pitch a fastball in half a second, kind of like how a human is pitching. It takes, a certain number of seconds or a certain fraction of a second to wind up and throw. This machine winds up. You put the ball in its hand and it winds up and throws in half a second. Separately, the other machine is a lot like the marble cannons we've been using. It's just spring loaded. The spring inside of it has a spring constant of 200 newtons per meter, and when it is being primed and a baseball is being loaded into it, the spring is compressed by 10 centimeters. So these are the technical specs of these two different machines, and we need to figure out the speed both of these things chuck baseballs at. Said baseballs having a common mass of 150 grams. Which according to the internet is the mass approximately of a regulation baseball. So, with the information we've been given, what thoughts, if any, do you have about how we can determine the speed these machines launch the baseballs at, given the things we're told about each one? So, my thoughts. Let's start with the spring. I feel like the spring is a little more obvious. For this spring, we know the spring constant and the distance it is going to be, the spring will be compressed. What formula can we use those things in to get some more information? And ultimately, there's only two formulas that I've taught you that have spring constant in them.
There's force of spring and then EPE.
All right. Spring force equals K times delta X, and EPE equals 1/2 K times delta X squared. So we have the information we would need to use either of these formulas to find spring force or EPE. And in the interest of being as not vague with you guys as possible, an earlier class asked me this question outright, and I'm not going to lie to my students. The test happened to be written in such a way that this formula never comes up. And so to keep you guys from accidentally pursuing the wrong train of math, I will tell you that for the upcoming test, you won't need this formula, and we also don't need it here, at least not the way that I intend this example to be worked. So you can put a little asterisk by that formula on your sheet that you won't need it on the test. I'm telling you this to try to keep you from being confused in the moment. And again, to honestly answer a question I was outright asked. So if we ignore that option for now, since we won't be needing it for this course, we can instead figure out how much EPE the spring would possess while compressed before firing. What would happen to that EPE upon pitching the baseball?
It would decrease.
Correct. As the spring fires and it returns to its normal size, the spring's EPE level would drop. So if we consider conservation of energy, total energy initial equals total energy final. Initially, we've got that amount of EPE, and that energy can't be destroyed, so if the spring doesn't have it anymore, where's it gonna go?
Through the baseball.
Into the baseball. And what form will the baseball possess that energy in?
Velocity, acceleration.
Velocity, or rather, to answer the question more specifically, the energy will be in the form of kinetic, which is the point of a pitching machine. You want to do work, use up energy so that the ball has energy in the kinetic state. Because it only moves, it only has a velocity if it possesses kinetic energy. So the point of a machine like this is to turn energy into kinetic energy inside of the baseball. And since we know the mass of the baseball, the kinetic energy formula can help us figure out the speed it'll be moving at when it possesses this much EPE, or rather, when this EPE becomes the same amount of KE in the baseball. Any questions on following the flow of energy? All right. So, our initial EPE is going to be based on what the spring was compressed to before being fired. So 1/2 times 200 times 0.10 squared, because we like meters instead of centimeters in here. When putting this in your calculator, make sure it is only the 0.10 being squared. Your calculator does not always get order of operations correctly. The KE formula, meanwhile, is 1/2 times mass times velocity, I'll write that down, times mass times velocity squared. So first was the EPE, then that's going to turn into KE, so 1/2 times mass times final velocity squared. We do know the mass of the baseball, so should we write 150 in there?
No,
No, what should we write?
0.150
Very good. And what unit would that be in?
kilograms.
Very good. And with that written, we can now solve for VF, which, considering that the 1/2s cancel, since there's a 1/2 on both sides, should look something like 200, bless you, times 0.10 squared over 0.150, square root of all that. And if my memory serves, please correct me if I'm wrong, should be about 3.65 meters per second, which is about the speed that our marble cannons were firing at for most tables. Maybe a little bit slower, but that kind of makes sense because the baseball has more, well, an equivalent mass, but is bigger. So, you know, consistent with the machines we've been using, pretty realistic. Now we gotta do the same basic thing to the pitching arm. The main difference being that that thing doesn't have any EPE in the beginning. Instead, the baseball is going to gain kinetic energy through a slightly different process. The ball will be gaining kinetic energy though. We just need to figure out how much it gains slightly differently. So instead for this arm, we know its power output and the time it will be using that power to accelerate the baseball. So what can we do with those pieces of information?
Power equals watts over time.
It is technically work over time. If the W is in a formula, it is work. If the W is a unit, it is watts. I do appreciate that is still weird. So I'll try to be very specific about it when I'm saying it out loud. The weird units will only continue as we start looking at things like momentum and different forms of rotational motion. So stay tuned for the Greek alphabet to follow. Anyway, for right now, we're just going to deal with power, work, and time. There's a second formula for power, but I'm going to choose to use this option for right now since we have time. And this would tell us the work the arm does. And the work that the arm does will ideally become the kinetic energy in the baseball. Because when you do work, you are using up energy and sending it somewhere else. And ideally, if we ignore things like friction, all of that work should become kinetic energy in the baseball. So, 1500 watts equals work over half a second. That means that the work output of this arm,
750.
thank you, would be 750 joules. And again, ideally, the baseball would be receiving all of that work as kinetic energy. Does that make sense? We treat it like conservation of energy again. Initially, the energy would be in a stored form inside of the arm's battery, probably. And eventually, after doing this much work, that energy would end up as kinetic energy in the baseball. That's the only place it's going. That's the only output here. Does that follow for now?
Yes.
Okay. Because that is the point of work, is sending energy somewhere in a different form. So, assuming that the ball is going to gain all of that energy in the kinetic form, we would set that equal as the kinetic energy final. And then for the formula itself, the 1/2 mv squared part would be the same. VF is still our unknown. VF should then be the square root of 750 over half of 0.150. And please correct me if I'm wrong again. I believe that comes out to be 100 meters per second. Assuming, again, all of that energy ends up in the baseball and we don't have to deal with pesky friction. Which means I think we have a pretty clear winner. That's about somewhere between a third and a fourth the speed of sound. So don't stand downrange with that thing. This thing would not be used in any sort of regulation NBA event. NBA is baseball, right? MBA. Major tag nabbit. MLB. I don't sports, if that isn't obvious. MLB, right?
Yes.
Yikes. NBA's basketball.
I like that phrase. I don't sports.
I don't sports. No. I can tell you all the math that happens in a sport, but I don't do the sport. I can perfectly calculate what angle a basketball needs to be thrown at, or what speed a baseball would need to be pitched at. I just have no appreciation or understanding for physically performing the task. Questions? All right. In that case, last thing I want to do today is refer to, there we go. The list you see when you click on the Test 1 tab on Brightspace. This is a summarized list of everything that we have covered over the past month and a half that will be on that first test. There's about 20 things on this list, but there's only 9 test questions because any given test question refers to, utilizes about 2 or 3 of these things, since they all feed into each other. So to briefly go over these, to set your expectation of what will be present. Very first thing we ever did was unit conversions, which you do need to be able to do, both the metric kind and also converting between different unit measurements of the same thing, so like miles into meters and things like that. Any weird conversions I will give to you. For example, there's a practice test question that asks you to turn miles per hour into meters per second, and I list in that question how many meters are in a mile. So you will have conversions like that. The only thing that you would need to be able to do, like know on your own, is the metric prefixes, but you can also write KHD based DCM on your equation sheet. Those. Oh, it's on the back page? I never looked back there. So yes, back page is also useful on your formula sheet. You keep forgetting that's there. After that, we started talking about vectors. And the first 3 vectors we discussed were displacement, velocity, and acceleration, utilized in these first 4 formulas. So this clump of 4 things really is just talking about the same thing 4 times. So on your sheet, that's referring again to these things. Know what they all mean, know the use case for each formula, be able to apply them to the motion of objects. Both 1-dimensionally and 2-dimensionally. 1D refers to forward and backward, 2D is forward and backward in 2 axes at once. Primary examples of 2D motion we looked at were projectile motion, which is any falling object moving through the air, and you can fall like this. So any question that involves an object falling straight down or possibly being launched counts as a projectile motion question, potentially a 2D projectile motion question. And to do those correctly, you have to analyze the motion in both axes simultaneously but separately. If something's a projectile, what is its acceleration automatically?
In the x-axis. x-axis, 0.
Very good.
And then the y-axis, gravity.
If something is a projectile, these two things are true about it automatically. That is true for things falling straight down. That is true for any question that mentions launching something off of a cliff or a roof or even just throwing it. If you haven't written this number somewhere on your sheet yet, I'd recommend doing that. You don't need to memorize it necessarily, but you may accidentally by the time this course is over anyway, if not already. The other type of 2D motion we've examined is vector addition, referring again to the practice of adding up a bunch of vectors together, possibly having to break them down into their components first to add x to x and y to y. So make sure you can do trig. And make sure you can take a vector like this, divide it up into its components, and then separately make sure you can take the two components and turn them into a hypotenuse and an angle. And that was everything up to chapter 3, I believe. Questions thus far? All right. On chapter 4, well, before that actually, remember again the difference between the acceleration of gravity and the force of gravity. This number is an acceleration, it is not force, and that means this number is not weight. If I ask you what the weight of an object is, or rather how to find it, what should your answer be?
Mass times force of gravity.
There, force of gravity is equal to mass times acceleration of gravity. So weight is force of gravity. Weight and force of gravity are synonyms. And those things are equal to mass in kilograms times the acceleration of gravity. By the way, again, g is this. Lowercase g is this. And if I ask you how do you calculate the weight of an object, and you just write m or you just write lowercase g, I will be sad. You will get partial credit, but I will be sad. Now, speaking of force of gravity, chapter 4 was about forces and the laws of motion. Again, you need to be able to identify the laws. You don't necessarily have to write them from memory, but you have to be able to look at a bunch of statements and know which ones are which and number them correctly. Using the laws of motion, we talked about net force, again, the sum of all forces which causes net acceleration. And you have to be able to draw free body diagrams, which again is just a picture of a box with arrows for every single force. So if I ask you for a free body diagram, that's just this. Frankly, if I don't ask for one, you should probably still draw one anyway if forces are involved, because I'm a visual learner and drawing it out helps me keep everything straight. The types of forces that we learned about that we've been putting on these drawings include, but are not limited to, actually no, they are limited to, the whole point of this list is to limit things. Gravity, tension, which is just rope force, and a pulley just exists to change the direction of it. Normal force, which again is the surface pushing back, and then friction, both static and kinetic. Be familiar with all of these types, be familiar with where they commonly live in pictures like this. I've also included the word inclines here, which is specifically referring again to just this notion. The idea that normal force and gravity are not always equal nor opposite, and that is epitomized in this scenario. Because on a ramp, the normal force always points out from the surface, which means it's no longer pointing up, even though the gravity still points down, because sitting on a ramp does not change anything about the core of the planet. In this scenario, the new relationship between normal force and gravity is that of this triangle. These are the same force arrows, I've just dragged gravity over here so that they're tip to tail. And the angle between the two is the same as the angle of the incline. I'm not just writing theta here twice because they are two angles, I'm writing theta here twice because it's the same theta both times. So if you know the angle of the incline, you know this angle between normal force and gravity. And gravity is always the hypotenuse of this triangle because normal force is always perpendicular to the other leg. The other leg being whatever forces are acting along the slope of the incline. So gravity is the hypotenuse. You may draw this triangle on your formula sheet. Again, same angle, same theta. I want to make that clear. Since normal force tends to change on a slope, the friction that comes from normal force also changes along with it. And that was everything in chapter 4. The last 3 things on this list are just the 3 things we spent the last week doing in chapter 5. Work, different forms of energy, and power. How do you guys feel? Does everything on this list sound okay for now? All right. That's pretty much it for today. It's Friday and I've been talking at you for a while, so I'm content to call it here for now. Do be studying and do please let me know what questions you run into while studying. Again, we will spend all of lecture next week going over any inquiries or issues you guys encounter. I will make sure you guys feel comfortable before the test. I have written the test to be such that you will be able to succeed at it. I do not want you to fail. I want to make sure you do good in this class. So, let me know if you need anything, and have a nice day.